If you've ever used a Python dictionary before, then you've used a hash table, which is a data structure that stores key value pairs and provides extremely fast data retrieval at big O of 1 on average. Today, we'll learn how hash tables work internally and why we are able to get such fast access times. It starts with the hash function, which is a mathematical function that takes in an input, or a key, and returns a fixed length integer called the hash code. The hash function provides us an index into the hash table, which is implemented as an array of buckets. Keys are passed into the hash function, and indices into the hash table are returned. In Python, if we add an entry to a dictionary with a key of name and value of Alice, the key will get passed through the hash function, which tells us where to store the entry. The entry is added as a node into the hash table with the key of name and value of Alice. We'll treat the hash function as a black box for now, meaning we won't worry about the internals of how it computes the index. We'll just be content knowing that it provides an index into the hash table. However, there are some properties of a hash function that are important to know. First, the hash function should be deterministic, meaning the same inputs should always give the same outputs. The same keys should never return a different index. The hash function itself must be quick to compute. This is essential for fast retrieval speeds. The hash function should return unique outputs for different keys. The same index shouldn't be returned for different inputs. In practice, this occasionally happens, and we'll see how to resolve it later. Let's see how we insert into a hash table. We want to insert an entry with the key of name and value of Alice. This is the syntax in Python. Name is passed into the hash function. Let's assume 2 is returned. The entry is then stored in the second index of the hash table. Next, we'll add an entry with the key of age and value of 25. This is the syntax in Python. The key is passed into the hash function, and this time we'll assume it returns 7. The entry is then added into the 7th index of the hash table. We get constant insertion time on average, since the hash function takes the same amount of time to compute regardless of the size of the key. When an index is returned, we know exactly where to put the entry. In other words, insertion time for hash tables is big O of 1 on average. What happens if we try to add an entry into an index that's already occupied? Where does the new entry go? This is called a collision and happens when the hash function produces the same value with different inputs. Collisions degrade performance. It takes us from constant time on average to linear time, or O of n in the worst case. There are 2 common ways to resolve collisions. First is chaining, where we store key value pairs in each bucket as a linked list. If we want to add a new entry, and our hash function returns another collision, we have to traverse to the end of the linked list to add the entry. This brings our insertion time to O of n in the worst case, since each time we have a collision, we have to loop through n elements in the linked list to add the new entry. We get constant insertion time if there are no collisions, and linear time if there are many collisions. Another common way to resolve collisions is open addressing, where we add our entry to the next available bucket. Let's try to add a new element, and assume that our hash function returns 2 again, which is already occupied. We have to traverse through the hash table until we find a bucket that's not occupied, and add the element there. We get O of n in the worst case again, since we have to traverse the hash table to find an empty bucket. This means that regardless of which resolution method we choose for collisions, we still get O of n in the worst case, which happens if there are many collisions. Let's talk about lookups now. This is the Python syntax to look up the value associated with the key age. It's the same process as before. The key is passed into the hash function, and we get the index of the hash table associated with the value. Lookup time is constant, or O of 1 on average. This is because the hash function gives us an index into the hash table, which we use to index directly into. What happens if we try to look up a value that was added as a result of a collision? In this example, our hash function returns 2 for the key city, which was added to the hash table using open addressing. We have to loop through the rest of the hash table to find the value associated with the key we're looking for. Again, this brings our lookup time to O of 1 on average, and O of n in the worst case. If we have no collisions, we get constant time. But if we have many collisions, we get linear time, since we have to loop through n elements to find the correct value. The result is the same if we use chaining. If our hash function returns 2 for city again, we have to loop through the linked list until we find the value associated with the key we're looking for, which degrades our lookup time to big O of n. The most important takeaway is that on average, hash tables provide constant lookup and insertion time with no collisions, and linear time if there are many collisions. This is why it's very important for our hash function to produce unique outputs for different inputs, since collisions degrade performance. Another important concept in hash tables is the load factor, which is defined as the number of stored elements divided by the number of total buckets. This is a measure of how full the table is. A load factor of 0.3 means 30% of the hash table is full. At this value, collisions are unlikely, but the table is sparse, meaning the hash table has many empty buckets that are needlessly taking up memory. Most hash table implementations aim to be at a load factor of 0.7 because it's a good trade-off between memory utilization and collision avoidance. At a load factor of 1, the table is full and collisions are guaranteed. A higher load factor increases the likelihood of collisions, which degrades the performance of the hash table. Most hash table implementations will resize the hash table when it reaches a load factor of around 0.7, meaning 70% of the table is full. This typically involves doubling the size of the hash table and rehashing each entry that was in the original table. This will bring the load factor back down, since we keep the number of stored elements constant, but increase the number of total buckets. Resizing and rehashing continues to happen as the load factor increases. Resizing is in itself a linear time operation, or O of n, since we have to individually copy each element into the new array. This is why most implementations try to keep the load factor around 0.7 to avoid having to perform this expensive operation. If you learned something, please consider following me on these other platforms. Thanks for watching.